Right, in this video we're going to describe and explain how the properties of polymers depend on their structural features. So the basic idea is the greater the chain length, the greater the intermolecular forces, which are based on van der Waals, since these are organic molecular compounds. And when you have those stronger forces, you're going to end up with a higher strength of your polymer and a higher melting point. So there's sort of two factors that we can look at that contribute to that. Number one is there branching present and how much is it? So as examples, we're going to use the low density polyethylene and high density polyethylene. So when you look at the two, what you'll notice is that the LDPE has a lot of branches. So you can sort of think of this middle one as like the main chain, and then you have these many branches. And the HDPE does not have that. So the difference is, if we're going to try and stack these together, which is what, essentially creating plastic is trying to lay together different layers of polymers, you can see that you could very easily just stack a second layer of HDPE on the other, and they can get very close together and fit very well together. Not the same case with LDPE. So they can't really get as close. So what happens is, in the HDPE, we're going to have a high melting point because we'll have stronger van der Waals. This can be strong, rigid plastic. And so therefore, a lot of our HDPE is found in our piping. Over here, the LDPE, this is like our plastic bags. You know that those melt at low temperatures. And so they're very flexible because they don't have those strong forces. Now, the second factor that we have is actually the orientation of methyl groups usually. We have atactic, which looks like this. So essentially we have our polymer, our main chain here, and what you'll see is that the methyl groups vary on what side they're on. So when they vary on what side they're on, it's going to be a little bit harder for them to fit together. They're not going to be able to fit together as closely. So when that happens, you again end up with a lower melting point. It's soft. And so atactic types of polymers end up being sort of used as like sealants, the ones that you can sort of squeeze out of your cylinder that would sort of seal the wall between your wall and like your bathtub or shower. And then we have the isotactic. So the iso is showing sort of that everything's on one side. So you see here the methyl groups all on one side. Therefore, when we try to stack these together, they're going to stack together more closely. So that ends up with a higher melting point. It's going to be tough. And so we often use this as fiber, bumpers, rope, things like that.